I'm going to take minus common from here. I'm going to take minus out from here and swap it. I'm going to reverse this by taking a minus outside and square it. So minus will all go off. And finally what I will get is nothing but the following. See if that makes sense to you. Is equal to Kp by 2 twice VDD minus mod VTP. Because I have taken minus and this is minus of minus VT, which we saw in the previous clip. So you can easily take minus outside and put it as mod VTP. So only a positive. Now you will take only the positive value of VTP when you open it into VDD minus V out, because we took minus common from here and swap the value. Same is the case here. Fair enough. So let's write R equivalent P finally as. So R equivalent P is equal to VDD minus V out upon Kp by 2. 2 will go up into ID of P, which I have found out here. This is ID of P, correct? So this is what we'll substitute there. This is not Kp into IDP, it's IDP. So IDP is now what I'm going to substitute. Kp by 2, 2 I have taken up, so this is Kp down into twice VDD minus VTP, VDD minus V out, minus here only VDD minus V out the whole square. So if you simplify this further by taking VDD minus V out common, it will be nothing but twice Kp twice VDD minus mod VTP minus VDD minus V out. Very simple, not to get intimidated by long terms. So I got R equivalent P, I got R equivalent N. Now I have to just connect in parallel to find the equivalent, and that we will see later. So this is region 2. Let's similarly quickly go ahead and find out for region 3. So in region 3 now, let's see the value of my V out. V out greater than VDD minus VTN but less than VDD. So let's find the region of operation. V out greater than VDD minus VTN. Yes, so NMOS is in cutoff. V out less than VDD. So PMOS would be in less than VDD means it's less than 1.8, correct? So it's surely greater than 0.6. So PMOS is in linear region because VDP is 0.6, correct? And V out is less than 1.8 but it's greater than 1.2, assuming 0.6 as VTN and VDD as 1.8. So V out is greater than 1.2 and mod VTP is nothing but 0.6. Again, positive value because of mod, so it's in linear. So we just saw in linear how to find R equivalent P. 2 upon Kp into twice, we just did this, VDD minus mod VTP minus VDD minus V out. So this is how we got equivalent circuit for all the 3 regions of operation. And now once we get all this, we can have R equivalent of N connected to R equivalent of P and draw a graph. Let's quickly do that. So suppose I draw a graph of resistance versus V out. This is 0. This is say VDD minus VTN or V out. That was VDD and this was mod VTP somewhere here. I'll find that my resistance irrespective of my V out will have a constant value, and that too a very low value, and this value will ensure, this very low value will ensure that there is very as good as no drop, and hence a perfect input can be passed as a perfect output because the value of the resistance does not change with respect to the output, and it creates a row resistance path where the value of the resistance is also very small, and hence we get the functionality in a CMOS transmission gate. See, you don't need to worry. This curve which I have drawn is nothing but R equivalent of N parallel to R equivalent of P. You can try this with the maths which we have done and you will come up with a similar graph. So this low resistance value, which is constant irrespective of V out and which is a very small value or a nominal value, will ensure that CMOS transmission gate gives us a perfect 1 and a perfect 0 at the output. Hope you have followed. Stay tuned, take care, and thank you very much.